Okay, welcome to Engineering Mathematics 1, and today we will be talking about a continuity of functions of two variables. So, we have already seen the definition of limit, indeed the delta epsilon definition of limit, and this is motivated by that definition. So, a function z is equal to f x y is said to be continuous at a point x 0 y 0 if this f x y is defined at x 0 y 0. Second, this limit x y goes to x 0 y 0 f x y exists, and the third one that this limit is equal to the function value at that point. If all these three conditions are met, so function is defined, this limit exists, and the limit is equal to the functional value at 0 x 0 y 0, then we call that the function is continuous at the point x 0 y 0. And if a function f x y is continuous at every point in the domain D, then we call that function is continuous in that domain D. So, eventually here the continuity is basically finding the limit as x y goes to x 0 y 0, and then observe that this limit should be equal to the function value at x 0 y 0. So, we can define delta epsilon definition as for the limit. So, a function z is equal to f x y is said to be continuous at a point x naught y naught if for a given epsilon there exists a real number delta positive such that this difference between f x y and the limit this value of f at x 0 y 0 less than epsilon whenever these x and y's we take from the delta neighborhood of x naught y naught point. So, this is the this was eventually the definition of the limit as well, where we have seen that this function has a limit L. So, this instead of f x 0 y 0 we used L there, and now since the function has to be defined at x 0 y 0 and we are looking at whether the limit of f x y as x y goes to 0 is equal to f x 0 y 0 or not. So, this epsilon delta definition is exactly the same as earlier for the limit. Indeed, here we have not used now that this must be greater than 0 to avoid this x naught y naught point, because now the function is defined at x naught y naught point. Earlier in the case of limit, function may not be defined at that point, still we can talk about the limit, but now in this case for the continuity the function has to be defined at x naught y naught, and therefore, this inequality at this end is no more required. So, there is another term we use for removable discontinuity. So, all the conditions we have discussed before, like the function is defined at x naught y naught, and the limit x y goes to x 0 y 0 f x y exists, and the third one when this limit is not equal to the function value at x naught y naught, then we call that the function has removable discontinuity. If this is equal, then this is the definition of the continuity we have just discussed. Let us go to some examples now. So, discuss the continuity of this function f x y is equal to 2 x 4 plus 3 y 4 divided by x square plus y square, and this is defined when x y is not equal to 0 0, and the value of this function is 0 when x y equal to 0, and we will discuss the continuity of this function at origin. So, we need to check basically that this limit here of this function 2 x 4 plus 3 y 4 divided by x square plus y square is equal to 0. If this limit is equal to 0, then the function will be continuous. Otherwise, in case this limit does not exist or this is not equal to 0, then we call the function is not continuous. So, as discussed in the last lecture, this changing to polar coordinate is very helpful for finding out the limit. So, in this case also we will follow those steps. So, we will change now from Cartesian to the polar coordinate, because whenever we see the x square plus y square term in the denominator, then this changing to polar coordinate is very useful. So, in this case, when we change the coordinate from x y to r theta, then x will be so we basically substitute here the x is equal to r cos theta and y is equal to r sin theta. So, by doing so, we got here 2 times r 4 cos 4 theta plus 3 r 4 sin 4 theta, and then here r square cos square theta plus r square sin square theta, which becomes here r square. So, now this r square will get cancelled with this. So, here also we will get 2, and now we have 2, or rather r square if we take common. So, we have here cos 4 theta plus sin 4 theta times r square. So, let us just see, and which, so this will become as the limit r goes to 0, and then here r square, and then cos 4 theta plus sin 4 theta, and since this is a bounded function cos 4 theta plus sin 4 theta, when r goes to 0, this limit will be 0, and the function value at 0 0 is also 0. So, the function is continuous. Function is continuous. Now, moving further to the next example, we will discuss now the continuity of the function f x y is equal to x minus y whole square divided by x square plus y square, when x y not equal to 0 0, otherwise at origin the function is defined as 0. So, in this case we will choose the path y is equal to m x, because here this choosing path is again conclusive, because the order here is 2, in y also it is 2, and there also it is 2. So, choosing y is equal to m x, the x will get cancelled and this limit will depend on m. In most of the cases this will work. So, when we do this substitution here for y is equal to m x, we will get this limit as x y goes to 0 0, and x and y is substituted as m x divided by x square and plus m square x square. So, from there we take common x. So, this x will be removed and we will get this limit 1 minus m whole square divided by 1 plus m square free from x. So, this limit which is x goes to 0 will be nothing but 1 minus m square by 1 plus m square. So, this limit depends on path, because choosing different value of m, we will get a different value of this limit, and hence this limit does not exist, and then again we will call that this function is not continuous. The next example, we will discuss the continuity of this function x square plus y square, the square root, and then we have here under square root x square plus y square, otherwise the value is 0, and we will discuss again the continuity of this function at 0 0, because when x y is not equal to 0 0, the function can be easily shown that this is continuous. So, at this point again, because x square y square term is there, changing to polar coordinate will be helpful, and we will do so. So, the limit x y goes to 0 0 sin this given function will be changed to as limit r to 0. So, here sin this x square plus y square will be r square. By that transformation, x is equal to r cos theta, y is equal to r sin theta, x is equal to r cos theta and y is equal to r sin theta. So, by this substitution we will get here r square, and here also this r square, and then this will be like limit r goes to 0, this is sin r, and here we have r. So, limit this sin r over r as r goes to 0, we have only one variable limit now. So, this using the for example, L'Hopital rule, we can get the derivative of sin r. So, that will be cos r, and this derivative 1, and limit r goes to 0. So, this will be 1. So, this limit here is 1, and the function value defined at 0 point is given as 0. So, the limit exists in this case, but the function is not continuous at 0 because this limiting value is not equal to the function value which is prescribed at 0. So, this is the case of the removable discontinuity, where the limiting value, so the limit exists, the function is defined, but this limiting value is not equal to the functional value at that point. So, this is the example of the removable discontinuity. Another example, we will discuss the continuity of this function again at origin. So, we have x power 4, y power 4, and then x square plus y power 4 power cube. So, now in this case we will choose this special path y square is equal to m x, because y is equal to m x will not be helpful, we have a different order here. So, now choosing this y square is equal to m x due to this y power 4 here. So, if y square will be then y m square x square, and then we can have this x square common. So, if we take this, we substitute this y square there, then in that case this limit x goes to 0, because this path will take to the origin only. So, now we will take the limit x goes to 0, we have there x 4 and then y square whole square. So, this will become x square and x power 2. So, m square x power 2, and then divided here by x square plus this y square whole square again. So, this is m square x square and power this 3. So, this x power 6. So, from here also x square and then power 3. So, x power 6 will be cancelled, and then we will get this limit m square over 1 plus m square cube, which is given here. So, this is m square over 1 plus m square over cube. So, again we see that if we choose this path, then the limit depends on the path. Again, for different values of m, we will get a different value of this limit, and therefore, this limit does not exist, and hence this function is not continuous. Now, moving next to the next problem, here we have the x square plus y square over 10 x y. So, looking at this function is difficult to see that what will be the limiting value, whether limit will exist, on what substitution we should make. So, again let us choose this y is equal to m x and see what is happening in this case. So, this given limit, if we have this x y goes to this 0 0, and then this x square plus y square over 10 x y, and if we substitute this y is equal to m x. So, we will take then the limit x goes to 0, and here we will have x square plus m square x square, and then this 10 m x square. So, y is m x, so x square. So, now when x goes to 0, we are getting like 0 in the numerator and also 10 0 0 in the denominator. So, 0 by 0 case, this is a one variable limit now. So, we can use basically L'Hopital. So, in that case we will get this limit equal to this limit 2x plus again 2x m square, and then here we will have the sec square m x square, and then this is 2 m x. So, this 2x and then also 2x from here will get cancelled, and when x goes to 0. So, this is 1 here, this is 1, and in this case it is there as m square. So, we have m square over this is 1, and this is So, 1 plus m square, this is 1 here, plus m square divided by m. So, again this limit is depending on the path, and this is 1 plus m square over m, which we have just evaluated there. So, limit depends on path, and hence the limit does not exist and the function is not continuous again in this case. So, some remarks which are very useful for finding out the continuity or basically the limit. So, changing to polar coordinate, as we have seen by substituting x is equal to r cos theta and y is equal to r sin theta, and is investigating the limit of the resulting expression as r goes to 0 is very useful, as we have seen in many examples. Like again, if we take the simple example x cube over x square plus y square. So, we can just change the polar coordinate. So, our limit will be the r goes to 0, and here we will have r square cos r cube cos cube theta over this r square, and then this r square will be cancelled with this r here. So, you will have r, and then limit r goes to 0. So, this cos square theta is a bounded function. So, here when r goes to 0, this limit will be 0. So, limit is 0. In another example, what we have seen, this changing to polar coordinate is also useful for determining that the limit does not exist. So, this was the case when limit exists. And now, in this case, when we substitute this again x is equal to r cos theta and y is equal to r sin theta in this. So, we will get here r square and here r square cos square theta. So, this r square will get cancelled with this r square, and in this case then there is no r left. So, this is cos square theta. So, this limit is cos square theta and it depends on theta. So, when the limit depends on theta, that means the limit does not exist. The limit should be independent of theta. So, here for different values of theta we are getting the different real number. So, this limit is not unique and hence it does not exist. So, we have seen other examples also that this choosing to polar coordinate is very useful for determining the limit as well as for determining that the limit does not exist. The next remark, that changing to this polar coordinate does not always help. Yeah, this is very important now, that it does not always help, and the transformation may tempt us to false conclusion. We will see some supporting example in this case. So, if we take this x square y over x 4 plus y square, this example, then if we substitute x is equal to r cos theta and y is equal to r sin theta. So, here we will get because one r square from here, r from here. So, we will get r cube and then cos square theta, here sin theta, and again here r 4 cos 4 theta and r square sin square theta. So, in this case this r square we can cancel out. So, we will get r cos square theta sin theta, and in the denominator we will get r square cos 4 theta plus sin square theta. And now, if someone just directly try to put the limit here and think that r goes to 0. So, this term becomes 0, we have something here sin square theta, and then here r cos square theta sin theta. When r goes to 0, that this becomes 0, but that is a wrong conclusion. Indeed, if we fix theta, so if we fix some value of theta, in that case this limit is 0, because whatever theta including 0 also, when theta is 0. So, this will become 0 and then everything will become this 0. So, the limit will be 0 in that case also. If we take any other theta, so some number will be sitting here and then r goes to 0. So, we can conclude that this is 0, no doubt about it. But the point to be noted here, that we have fixed theta. So, for fixed value of theta, this is 0. But as for the limit, we have already discussed that we should not fix theta to conclude that this is the limit. Fixing theta means fixing the path. So, in some particular path this limit is 0, where we are fixing the theta. It is like the straight line, the case of the straight line. When we are fixing the theta, we are basically approaching towards. So, if we have, this is our r theta plane, and then by fixing theta. So, if we have fixed theta and then approaching to origin here, in that case we are basically approaching to origin by the straight line. So, again this fixing theta will not conclude that the limit is 0. So, for example, if we take another path where y is equal to x square path. So, this is again going to 0 to origin, and in this case if we choose this particular path y is equal to x square, or in polar coordinate r sin theta is equal to r square cos square theta, then this limit will become r goes to 0, and here this x square r square cos square theta, and then this r sin theta, again we have used this r square cos square theta, same thing here r square cos 4 theta, and this r sin theta is replaced with r 4 cos 4 theta. So, now what are we getting here? It is r 4 cos square theta, and again cos square theta and cos square theta. So, we are getting here r power 4 cos 4 theta, and here we are getting 2 times r 4 and cos 4 theta. So, this will get cancelled and we will get this limit half, or directly one can see just substituting y is equal to x square there, taking this path. So, we will get that limit, the desired limit, as x goes to 0 and then x square. So, y is replaced by x square, and then we have x 4 and plus y square, again here x 4. So, again this x 4, and so limit x goes to 0, and we have this x power 4 divided by 2 x 4. So, x 4 get cancelled, and then we get this limit half. So, this is the limit in this case along this particular path, while by not closely looking at this here, we could have done this mistake by taking this limit here as r goes to 0, and then this limit is 0, but this is not the case, as we have seen that this is indeed 0, but in that case we have to fix this theta, and then the limit is 0, and we have anyway seen here by taking this path the limit is half. So, limit does not exist in this case, and we will discuss now the continuity following by that motivation, the continuity of this x square y square over x cube plus y cube. And in this case, if we change the coordinate to this polar coordinate, what will happen now? So, this is r square. So, r 4 will come and cos square theta sin square theta, and from here r cube will come. So, we have 1 r in the numerator, and then cos cube theta and sin cube theta. So, again when r goes to 0, we should not do that mistake that r goes to 0 and something is here. So, it becomes 0. No, we have to closely look at this function, whether it is if it is a bounded function of theta sitting here, and then we are taking this limit r goes to 0, then this will be 0. But in this case, this function here, for example, this cos cube theta minus sin cube theta may become unbounded, because this may go to very close to 0, and this is actually unbounded function. So, this is not a bounded function. So, we cannot use that fact that this limit as r goes to 0 is 0. So, if we fix theta, if we fix theta, then again like in the previous example, this limit is 0. Thus, we cannot conclude that the limit is 0. So, we will see in the next slide now again that limit in this case does not exist. So, if we look at the continuity of this function, so along this path y is equal to mx, or fixing theta, it is the same thing. So, we will get this limit as 0. So, we take y is equal to mx, or changing to polar coordinate and fixing theta, as we discussed both are equivalent. So, here this limit is 0 along this path, But if we take this special path y is equal to minus x e power x, then we are getting here x square, and for y square again x square e power 2 x, and then x cube, and this y cube will be x cube with minus sign and e power 3 x. So, now in this case this x cube will get cancelled. So, we have in the numerator x e power 2 x and denominator 1 minus e power 3 x. So, what is the limit here? X goes to 0. So, it is a 0 by 0 case. So, we can use the L'Hopital rule. So, this limit will be equal to, so e power 2 x plus x as it is, e power 2 x and then 2. So, this is a differentiation there, and then minus e power 3 x into 3. So, when x goes to 0, this goes to 0. So, we have 1 over 3. So, minus 1 over 3 is the limit of this function along this particular path. Again, this path is going to 0. So, we have taken a very special path to show this is a very typical example and difficult to realize that along this path we will get a different limit, but this proves that the limit does not exist and hence that function is not continuous at 0 0. The last example we will discuss here the continuity of this function at origin. So, again we change to the polar coordinate, it will simplify this x square plus y square term, and we have x y goes to 0 0 e power minus 1 over x square plus y square x 4 plus y 4. So, changing to polar coordinate, it will be like e power minus 1 over r square, and this here this will be r 4 and cos 4 theta plus sin 4 theta because of this term. So, now here we can do little bit manipulation. So, here cos 4 theta plus sin 4 theta we can just make a square term here. So, the cos square theta plus sin square theta whole square. So, the 2 times cos square theta will come, and then minus we can subtract that cos square theta plus into sin square theta. So, this term is equal to this term, the whole square minus 2 times cos square theta sin square theta, because when we open this square we will get cos 4 theta plus sin 4 theta and 2 times the product, which will be cancelled by this one. So, we will get this term. So, that sin square theta plus cos square theta became 1 here, and then we have this 1 minus this term, which again we can write down here 2 times cos theta sin theta as sin 2 theta. So, this is square, because of the square will appear here, and we have to make this 4. So, we multiplied and divided by 2. So, we have this term now. So, we have to see what is this limit here of this function. So, what is the limit? So, in this case we have to note now that this 1 minus half sin square 2 theta, this term here lies between half and 1. So, this is like 1 when theta is 0, and then this half when this sin square theta is 1. So, this will become as half. So, this lies between half to 1. So, in this case then for r not equal to 0, we can estimate this term, the whole term there 1 over r square and 1 minus this one. So, this is a positive term, this is a positive term, and here also we have this is greater than half. So, certainly this is greater than 0, and also now because we know that this is always greater than half. So, we can replace this half also and get the upper bound for this term. So, replacing this by half, we will get this 2 e power minus 1 over r square over r 4. So, this term here lies between 0 and this term. And now, for this we can look at what is the limit of this as r goes to 0 of this 2 e power 1 over r square r 4, which we have just used another variable t here, which goes to infinity, because 1 over r we are substituting as t. So, if r goes to 0, t will goes to infinity. So, here we have 2 e power minus t square, and then this 1 over r 4 will become t 4. And this we can now handle easily. So, this is 2 t power 4 and e power t square. So, infinity by infinity case, and then we can use L'Hopital rule with to get this limit as 0. So, this limit is 0. So, what we see that this term here which we want to get the limit as r goes to 0, this is between 0 and something here which again goes to 0 as r goes to 0. So, by this squeeze theorem or sandwich theorem, we can get now the limit this as, because this is 0 and here also in the limiting scenario this is also going to 0. So, this limit has to be 0. So, in this case now we can conclude this. So, we have discussed the continuity that f x y is equal to the limiting value here is equal to the function value of that function, then we call that the function is continuous, and naturally the function must be defined at this point, then only we can talk about the continuity. And what we have also observed that we need to be very careful while changing to polar coordinate, because that may mislead to some wrong limit in many cases. So, these are the references we have used to prepare these lectures, and thank you very much.